Hi goers, welcome to the Chapter 1 review video. This is the first one, part 1 of 2, and this video we're going to cover functional groups, hybridization, chemical bonding, dipole moments, all the very basic things that you'll come across in Chapter 1, and the next video is going to cover resonance. So the first thing we're going to delve into is functional groups, and functional groups are basically just a series of atoms, so it's a very specific atom connectivity located within a larger molecule, and that specific atom connectivity has a specific type of reactivity associated with it. So you'll see that we have a whole bunch of functional groups, in this class that we're going to talk about, but we're not even really going to talk about all of them. There's a lot more that are beyond the scope of this class, but each chapter is going to get a specific functional group, and we're going to see all the different reactions that are possible with that specific functional group, and that's pretty much organic 1 and organic 2. So let's just start with A, identify the functional groups in the flavin adenine dinucleotide molecule. So FAD is something you may have come across. It's an electron carrier in the body. It can be oxidized and reduced. So within this molecule, there's going to be a whole bunch of different functional groups. So let's just start with labeling A. So A is a 6-membered ring with alternating single bonds and double bonds. So that is a benzene. That is a benzene. Okay, and sometimes benzenes are also called arenes, A-R-E-N-E, okay? So B is going to be an alcohol, okay? So an alcohol is a carbon to an oxygen to a hydrogen. So alcohols have to be further classified because there are many different types of alcohols, and we classify these alcohols based on the carbons that are directly attached to the carbon in this functional group. So most people think that OH is an alcohol, but really it's COH, which is an alcohol. So the carbons attached to that carbon would be this one over here, that's carbon number 1, and that would be carbon number 2. So that's what we're going to call this a secondary alcohol, okay? In C, we have a carbon-oxygen double bond called a carbonyl, and directly adjacent to that is a nitrogen. So this is called an amide. Okay? Then we move to D. So D is a carbon-oxygen single bond with another carbon-oxygen single bond. So this is called an ether. Okay? In E, we have a carbon-carbon double bond. So that's called an alkene. And alkenes are going to be the first functional group that we kind of look at their reactivity starting in Chapter 6. And then F is just a nitrogen to carbon single bond. So this is called an amine. And just like alcohols, amines have to be further classified because we can have many different types. So amines are just the number of carbons that are directly attached to the nitrogen. So we only see that there is one carbon here, so this would be a primary amine. Okay? So I hope that kind of opens up your eyes to some of these functional groups in specific biological molecules. And then we can also show you like some sort of organic medication that is synthesized in a lab. And here we have captopril, and that is going to be, a medication that lowers your blood pressure. So if we were to zoom in over here, we see that G is going to be a carbon-oxygen double bond with an oxygen and a hydrogen directly attached to that carbonyl. So this is a carboxylic acid. Okay? And then H is going to be a carbon to sulfur to hydrogen bond, and that is going to be called a thiol, sometimes called a sulfhydryl, but in your class we'll just call it a thiol. Okay? So I think that pretty much sums up how to identify these functional groups. You just really have to memorize them. They're not too bad. And again, you have to know all the functional groups that are located on the front cover of your textbook. Any of those can come up on the test and they are fair game. Okay? So that pretty much sums up functional groups. So the next thing we're going to talk about is hybridization and chemical bonding. So, this is a very, very complex topic, hybridization. We typically don't cover the fundamentals in terms of quantum mechanics and the orbital theory and all that stuff. So we're going to give you a very brief version of what hybridization is and how that relates to chemical bonding in organic molecules. So what is the concept of hybridization? So basically, I'm just going to take you back to Gen Chem here for a second. And if we were to say, what is the electron configuration of carbon? So we said with carbon, if we look at the periodic table over here, it's over here, we would say that it's 1s2, 2s2, and 2p2. So let me write that out over here. 1s squared, 2s squared, and 2p2. So we wrote that in, I guess, Gen Chem, and we were like, what does that mean? Well, we know that carbon has all of these atomic orbitals associated. We have an s orbital in the first row that is completely occupied. We have an s orbital in the second row that is completely occupied. And we have 3 p orbitals in, the second row as well, and not all of them are filled. Only 2 electrons are located there. So what does this really mean? What are the orbitals that are involved in bonding? So these are atomic orbitals, but then there are, hybrid bonding orbitals. So we have to kind of make that clear right now. So basically, we said back in Gen Chem that the valence orbitals are the ones that participate in bonding. So those are the ones that are in the outermost shell. And that makes sense because those orbitals are, most accessible to coming into contact with other atomic orbitals. So basically, we can consider just the orbitals that are in the second row, so the s and the p orbitals. And let me just draw a little energy diagram over here to, show you where that is. So this is energy, and s orbitals are lower than energy than p orbitals, and there are 3 types of p orbitals. So remember when we were drawing those boxes, you may not have known, why am I drawing 3 p boxes, and why am I drawing 1? So basically, there's something called degeneracies, and there can be 3 equivalent p orbitals, all of equal energy. They just exist in nature, so whenever you see a p orbital, there really are 3 types of p orbitals. Okay, so this is my 2s orbital, this is my 2px, my 2py, and my 2pz. Okay, so if I were to fill in the electron count, we have 2 electrons in the s orbital, and we have 2 electrons in the p orbitals. So this is what it would look like. So what does this mean? Are any of these p orbitals or these s orbitals involved in bonding? And the answer is no. So the concept of hybridization is that these individual atomic orbitals are going to hybridize or morph together to form hybrid orbitals. So literally, you will see something that looks like this. Okay, so these s and 3p orbitals are literally coming together and hybridizing to form 4 equivalent energy sp3 orbitals, okay? So notice how I purposely put the sp3 orbitals in a lower energy setting than those p orbitals, because there's a reason why chemical or atoms like to bond. Atoms like to bond because they lower the overall energy of these individual atomic orbitals, okay? So that's why hybridization occurs. So with these sp hybridized orbitals, they can come in 3 different forms, like we'll see, that are the ones that involved in bonding, okay? So I hope that makes it a little bit more clear. So if I were to draw, maybe like a little diagram of this, we have a carbon here with these 4 sp3 orbitals attached to them. Okay, and that little circle is the s character, and the kind of lobular part is going to be the p orbital, so that's kind of showing the notation of hybrid orbitals. Those, these are all sp3 orbitals, and then they're going to come into contact with other atoms, so maybe let's just say a hydrogen here. So this is the hydrogen 1s orbital, and when they come into contact with each other, that is what's going to form a bond. And you can have these hydrogens come from all different sides. And they don't have to be hydrogens, they can be other, atoms like carbons or, fluorines or things like that. And it's the bond between the hybrid orbitals and the hybrid orbitals of the other, atom that are going to form a bond, okay? So that's pretty much the overall concept of hybridization. Okay, so there are 3 types of hybridization, so let me make more space over here. Okay, so there are 3 types of hybridizations that exist. There are the sp3s, the sp2s, and just the sps. Okay, so there are just 2 things that you need to know about all these different things. So sp3 orbitals have tetrahedral electron geometry. Tetrahedral electron geometry. Okay, and sp2s have trigonal planar electron geometry. Okay, and sp orbitals have linear electron geometry. Okay, and the last thing you need to know are the bond angles. So every time you see an sp3 center, you can say that they're going to have approximately 109.5 degree bond angles. And I said approximately because there can be other factors that, may diminish that bonding angle, such as repulsion. So, you see with water over here, we know that that oxygen is an sp3 center, and I'll be able to show you how to identify that in a second. But it should be predicted to be 109.5, but in theory, it's really 104.5 because of factors like the fact that these two lone pairs are so close together and their repulsions. So for this class, we're not expecting you to know like the specific bond angles of, molecules, but a good idea of the electron geometry is important. So 109.5 approximately. And for the sp2 centers, we're going to have 120 degree bond angles. And for sp, we're going to have 180 bond angles. So I would just memorize those facts about these centers, and you'll be golden. Okay, so now I want to delineate between ethane versus ethyne. Okay, so right now you don't really know what these compounds are in terms of their chemical formula, but ethane is going to be C2H6. Ethene is going to be Ethene is going to be C2H4, and ethyne is going to be C2H2. Okay, so these are three different types of molecules, and I want to talk about their bonding. So with ethane, when we saw that energy diagram, I'll just redraw it again, there was 1s and 3 p orbitals, 2 p orbitals, so I'll just say the 2s over here, 2px, 2py, and 2pz. And I were to fill in that electron count, we said there was 2 here, 1 here. And what happens with ethane is that all three of these s and p orbitals are going to hybridize to form four equivalent sp3 orbitals. Okay, so we are going to have 4 equivalent sp3 orbitals, each with 1 electron attached to it, so this molecule can form 4 additional bonds with other molecules. Okay? So that's what ethane is going to look like. So we showed that picture earlier. Let's say I have, this carbon over here to this carbon over here. This carbon-carbon bond is a result of sp3 orbitals overlapping. So if I were to just maybe zoom in over here, I can kind of draw you a little diagram of that. So we have a carbon with its sp3 orbital and another carbon with its sp3 orbital, and they overlap. And this overlap is what's forming that carbon-carbon bond, okay? And then, we said that there are 4 on each of these carbon atoms, so if I just draw the remaining 3, now the hydrogen 1s orbitals, so those look like spheres, this is the hydrogen 1s orbitals, I'll just draw circles to delineate that. So we said that there are 6 of them, and those are going to overlap with the sp3 orbitals of each of these carbons to form more bonds. Okay? So that's the bonding pattern for ethane. And, this is the orbital diagram, but it's more commonly written as something like this. Okay, so that is ethane. So C2H6, and now we kind of can rationalize what those bonds really mean. So there's more than just this Lewis structure. We really can see now that there are carbon sp3 orbitals, overlapping with one other carbon sp3 orbital to form this bond over here, and then the remaining carbon sp3 orbitals are going to bond with those hydrogen 1s orbitals, become completely saturated. Okay, so that's ethane. So now let's consider ethene. So let me erase this. Okay, so ethene has a little bit of a different scenario. So instead of all the p orbitals and the s orbitals hybridizing to form hybrid orbitals, we are going to have only 2 of the p orbitals involved in that. So instead, we're going to see something that looks like this. Okay, so if I were to fill in the electron count here, you can see that we are left with 1 unhybridized p orbital. And we're going to be able to see what that p orbital is allowed to do in terms of chemical bonding. So we said that there is a maximum of sp3, meaning that there's 1 s orbital and 3 p orbitals that are maximum allowed to morph together. So in this scenario, we only decided to use 2 of those p orbitals. That's why we have sp2 hybrid orbitals. And since we didn't use that third, it's just going to hang out at a higher energy state, okay? So I'm going to draw the specific bonding pattern of this, down here, just like I did for ethane. So we have that carbon and we have that other carbon. So we understand that there's going to be a carbon-carbon overlap, so that's sp2 and sp2 orbital overlap. And then we said that there are going to be 3 on each of those carbons. So there's going to be this one, there's going to be this one, there's going to be this one, and that one. Okay? So these are all the sp2 orbitals of each of those carbon atoms. Okay? And then we can show that the hydrogens, so we said that ethane is going to be C2H4, there's going to be 4 hydrogens, and these are the hydrogen 1s orbitals. So now we can kind of have an idea of which orbitals are involved in these bonds. Okay, but now we talked about all the sp2 orbitals, but what about that extra p orbital? What does that do? So I'm going to draw it in a different color, so let's call it blue. So the p orbitals, you know, they're dumbbell shapes, so they look like this. And that extra p orbital on each of those carbon atoms is now capable of forming a bond with the other adjacent carbon. So for instance, it's going to form a bond up here. So now we see that these extra p orbitals are the ones that are involved in forming pi bonds. Pi bonds are just the bonds that form in addition to the sigma bond. And it's called pi because they are from p orbitals. So this is the pi bond overlap. So I'll just say p orbital, and that's going to form a pi bond. So if I were to draw, you know, the Lewis structure of that, it's going to look something like this. Okay? So now we know that these are sp2 carbons, each with 3 sp2 hybrid orbitals, and we see that we have an additional bond to the carbon, which is a result of those p orbitals overlapping. So I hope that makes sense with a better picture. So finally, let's consider ethine, so that's C2H2. Erase over here. Ethine. So ethine has a different situation as well. So let me just erase these. And instead of the 3 p orbitals or the 2 p orbitals morphing together, we're only going to have 1 p orbital morph together. So that is going to look something like this. So we have sp, sp, and there's 1 p and another p. Okay? So again, we have a maximum of sp3 or 1s and 3 p orbitals that can morph together. And in this situation, it only chose to do 1s and 1 p. So we're left with the 2 remaining. Okay? So again, filling in those electrons over here. So let's see what that kind of looks like. So we have a carbon to carbon bond over here. Oops. Okay, and we are going to see that we have this sp overlap, so that's an sp and an sp. And then there's one more on each. Okay, so we said it's C2H2, so that means that there must be 2 hydrogens that bond here, so that's a hydrogen 1s, like again. And if I show these bonds forming, so then what happens with those extra 2 p orbitals? Okay, so we have 1 over here. Okay, and then we can draw another one in another color, and this way. So we can call this one maybe py, and we can call this one px. Okay, so now since we have these 2 extra p orbitals on each of the carbons, we can form 2 additional carbon-carbon bonds. So we can see something like this. The blues overlapping and the purples overlapping. So you see how there's 3 lines in between those carbons. So if I were to draw the Lewis structure of that, it would look something like this. Okay, so maybe now that makes a little bit more sense of what hybridization is and how it works in terms of bonding. Okay, so that is the concept. So let's move on to specific examples of that. So metoprolol is a beta blocker responsible for preventing or suppressing heart arrhythmias. For the atoms depicted below labeled I through L, identify the hybridization, bond angle, and molecular geometry. Note that lone pairs are not depicted in these structures. Okay, so let's just go through this and kind of write in where our lone pairs are going to be. So on our oxygen atom, we have 2 sets of lone pairs. And how do I know that? Well, oxygen likes to have 2 bonds and 2 lone pairs associated with it, so we see that there are 2 bonds, so that means that there must be 2 lone pairs left over. On this oxygen, likewise, we see that there are 2 bonds already, so there must be 2 lone pairs not drawn in. This oxygen has 1 carbon bond and 1 hydrogen bond, so this also must have 2 lone pairs that need to be drawn in. And nitrogen likes to have 3 bonds and 1 lone pair. So nitrogen is already bonded to a carbon, and another hydrogen, so we would just draw 1 lone pairing. Okay, so how do I decide the hybridization first? So for me, I like to do something called the areas of electron density. So I like to just count the regions where electrons are located, and then that's going to give me some insight on what the hybridization is. So we see that there is one bond to oxygen, another bond to oxygen, a lone pair to oxygen, and another lone pair to oxygen. So those are 4 total areas of electron density. So that means that my powers are going to have to add up to 4. That means S1P3, because 1 plus 3 is 4 total areas. So now we know that this is going to be an sp3 center, okay? So let's just leave that there. Let's go to J. So J has one lone pair, another lone pair, one bond, and one more bond. So that is an sp3 center. If you're saying, wait, it's not an sp3 center, you're right. Why isn't it an sp3 center? Well, there's something called resonance, which is going to change, the hybridization pattern. So we like to take the lower hybridization scheme because those tend to be the more stable configurations. So one of these lone pairs can actually resonate in to this benzene molecule and, force these electrons up. So if I were to just write, a quick version of that, it's going to look something like this after it resonates. So now let's count the electron density areas after we resonated with the benzene. So that's one lone pair, one pi bond, and one single bond. So that's 3 total areas, or S1P2. Okay, so that's an sp2 center. Let's move to K. We have one lone pair, another lone pair, one single bond, and another single bond to the hydrogen. So that's 4 total areas, no resonance possible. So that's going to be an sp3 center as well. So let's look at the nitrogen. There's one lone pair, one single bond, and one more single bond. So that's 4 total areas, no resonance possible. That's also going to be an sp3 center. So now that we have the hybridization, everything else is pretty much self-explanatory. So if I were to fill this in on the chart over here, we have sp3, sp2, sp3, and another sp3. And then the bond angles are going to just match what you already know. So bond angles for sp3 centers are 109.5, 109.5, and 109.5. And bond angles for sp2 centers are 120. And we said that the electron geometry, keyword electron geometry, reflects the hybridization. But this is asking for the molecular geometry. So molecular geometry is going to take you back to Gen Chem, where remember we did Vesper theory and we said, something like AX2E2 is bent. So you have to just do those with these molecules, and that is the molecular geometry. So just be careful on the test because some people get electron geometry and molecular geometry confused. Electron geometry is going to reflect the specific hybridization scheme of that atom, and molecular geometry is going to reflect the amounts of the types of bonds and lone pairs, so like the AX2E2 type configuration. So let's just do that for all of these down below. So for I, we see that we have 2 bonds attached to it and then 2 lone pairs, so that's AX2E2. And that is a bent molecule, so that's bent. Okay, so for J, we see that we have AX2, so there's 2 bonds to oxygen. So we don't count the double bond twice, it's just 1 bond. AX2E, that's also bent. For K, we see that we have AX2E2, that's also bent. And then for L, we see that we have AX3E. So AX3E is pyramidal. Okay, so you can fill that in on the chart. So we would say that we are bent, 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 and pyramidal. Okay, so that's how you do hybridization, bond angles, and molecular geometry. Pretty easy. So let's move on to D. So furane is a common chemical solvent that you may come across while you're in the organic lab. So the first thing we want to do is identify the orbital overlap for the bonds labeled M through O. And if there is more than 1 bond present, we want to identify all the orbitals involved in forming those types of bonds. Okay? So the first thing you want to do with this is classify the hybridization scheme. Okay? So let's look at M. So M, we looked around those lone pairs, so there are going to be 2 lone pairs on the oxygen. On that oxygen, we see that there is 1 lone pair, another lone pair, 1 single bond, and 1 single bond. So we're thinking sp3. However, is there any resonance possible? Well, yeah, there is resonance possible. We can resonate one of those lone pairs into the ring, and push that pi bond out. So the resonance would look something like this. Okay? So again, I'm going to draw the other structure over here. So we just formed a molecule that looks like this. Okay? So with that structure, that's what we want to consider with the orbitals. So now oxygen's new hybridization scheme is going to be one lone pair, one pi bond, one single bond, or sp2. And then this carbon, don't forget that there's an imaginary hydrogen there. So for that carbon, I'll just draw the areas in purple. One pi bond, one single bond, and another single bond. So that's going to be another sp2 center. Okay, so we know that the sigma bond between those is going to be a carbon sp2 and an oxygen sp2 overlap. So something that looks like this. So let me just draw it over here. It's going to be carbon sp2 with an oxygen sp2. Okay, and that's the sigma bond. But then now we see that there's an additional pi bond present. So that pi bond is a result of the p orbitals. So that's going to be a carbon 2px with an oxygen 2px. And you don't need to say that there is going to be, you don't have to say that they're always x. You can say that they're both y's or they're both z's. But the situation is you have to say that they're both the same letter because that means they're in the same 3D orientation for orbital overlap, okay? So for M, we have these two bonds. We have the carbon sp2, oxygen sp2 overlap, and we have the carbon 2px with the oxygen 2px overlap. That's M. So for N, we see that we have a single bond, carbon to hydrogen. So what is that orbital overlap? So if we were to classify this carbon, it is one pi bond, one single bond, and another single bond, so that's an sp2 center. And since hydrogen only has one bond to it, and there aren't other atomic orbitals present, hydrogen is always going to be 1s. There is no hybridization possible with hydrogen, because think about it, hydrogen on the periodic table only has 1s. So if there's no other atomic orbitals to hybridize with, hybridization is clearly not possible. So here we would just say that the orbital overlap is going to be a carbon sp2 with a hydrogen 1s. Okay, so then let's look at O. So for O, again, we just decided that those carbons are both sp2 centers, so we can say that the sigma bond there is going to be the carbon sp2 with another carbon sp2, and the pi bond is going to be those additional p orbitals. So it's going to be something like carbon 2py. I just chose the y's at random, carbon 2py. And that is the types of bonds that are going on in M and in O. Okay, so now, someone might say, why is it that I couldn't resonate the other lone pair on the oxygen to the right and get an sp center? Okay, so there's an issue with why I can't do that, and I will show that right here. Okay, so if I were to resonate this in and push those up, and then resonate these in and push those up, the resonance structure for that would be something that looks like this. Okay, so this molecule is extremely unstable for a couple different reasons. Look at that formal charge, number one. But number two, the issue is that an sp geometry like this one, because there's one double bond and another double bond, predicts what type of bond angle. Well, it's 180 bond angle, and there's no possible way to get 180-degree bond angles in a ring, because you're forced to be in this, angled orientation, not linear. So that's why you can't resonate both. So that's going to bring us to our second part of the oxygen atom in furan has two sets of lone pairs. Identify which orbitals house each set of lone pairs. Well, clearly we just showed that only one of those lone pairs is allowed to resonate, not both. So that means the one that is allowed to resonate is going to be the p, it's going to reside in a p orbital, and the one that can't resonate is going to stay in a hybrid orbital. So you could just say that this one, because I decided that it resonates, is going to be in a p orbital, and this one is going to be in an sp2 orbital. Okay? So I hope that makes more sense on the type of bonding that is present in atoms and molecules. Okay? So the next concept we're going to move on to is types of bonds and dipole moments. So we have this Pauling scale of electronegativity, and basically it's just showing us these arbitrary values that are assigned to different atoms. And the concept is that you want to take the electronegativity value of the high minus the electronegativity of the low, and that is the change in electronegativity, or the difference in electronegativity. And then there are certain cutoff values that we know for chemical bonds, and we can classify these chemical bonds based on the delta En. So what you need to know for your test are these specific cutoff values. So I'll write them below. So if your delta En is going to be less than 0.5, we're going to call that nonpolar covalent. And we know it's covalent because we have two atoms that are sharing electrons between each other, but we're classifying them as nonpolar because that electronegativity value is not sufficient enough to basically induce a dipole in that molecule. So it's nonpolar, or not pulling. Okay? So then if your delta En is in between, actually let me move that over a little bit. If your delta En is going to be between 0.5 and 1.9, then that's going to be classified as a polar covalent bond, because that is sufficient enough to, cause a dipole in the molecule. Now, I did want to say something now where the equal sign matters. So if the delta En is equal to 0.5 or equal to 1.9, that is still a polar covalent bond, but the minute you go a little bit below 0.5 or a little bit above 1.9, you are not considered that anymore. Okay? And then if your delta En value is going to be greater than 1.9, so delta En greater than 1.9, we're going to call that an ionic bond. Okay, this is pretty self-explanatory. All you have to do is subtract the highest from the lowest. So for carbon, we see for the first one, classify the following bonds as either non-polar covalent, polar covalent, or ionic. Carbon is going to be 2.5, and hydrogen is going to be 2.1. So let's do that. 2.5 minus 2.1 is going to be 0.4. 0.4, according to our values, is less than 0.5, so we're going to call this bond non-polar covalent. Okay, let's do magnesium and chloride. So magnesium is going to be 1.2, and chloride is going to be 3.0. So 3.0 minus 1.2 is going to be 1.8. So 1.8 is a little bit less than 1.9, so that's going to be considered a polar covalent bond. Okay? Then we're going to do the phosphorus to oxygen bond. So phosphorus is 2.1 and oxygen is 3.5. So 3.5 minus 2.1 is going to be 1.4. And 1.4 is also less than that 1.9 value, so that's going to be polar covalent as well. Okay? So that's how you do classifying these bonds. Not too hard. Okay, so the last thing we're going to talk about is dipole moments. So, we just use those electronegativity values on the Pauling scale to decide what types of bonds are there. So we can just do this, in a quick fashion by seeing, is there an atom that's different, or an electronegative atom that's different from carbon or hydrogen, and those are going to be ones that pull, okay? So we see over here in this NATA projection, I can zoom in, that we have a dipole in the orientation towards that bromine, and then we have another localized dipole in this orientation towards that bromine. So we can do vector addition. So if I drew those arrows head to tail, then the resultant is going to be this arrow. Okay? So in theory, we're going to have a dipole moment for this molecule to be like that. Okay? So let's do it again for this next molecule. So we have a localized dipole towards that chlorine. We have a localized dipole towards that chlorine. So if I were to, draw those two arrows head to tail, the resultant is going to look something like this. So that's right through the middle. So that's that dipole moment. Okay? For the last one, we see that we have a dipole moment coming up and out of the page like this. Then we see a fluorine going down and into the page, and then we see this fluorine coming down and out of the page. So clearly, this fluorine over here with this fluorine over here are going to cancel. So this is negligible, that's going to be negligible. And then this fluorine is the only one that doesn't have anything that cancels it, so the dipole moment is really straight down and out of the page. But you don't have to draw out of the page, just straight down. Okay? So that is it for, I guess, pretty much 90% of Chapter 1. And the next video is just going to focus on all the resonance problem that we did. So I'm just going to do the worksheet over again in that video. All right, good luck.